Okay, we're going to be talking about circular motion. Most people are taught that acceleration centripetal acts towards the center, while velocity instantaneous is tangent to the circle, and quite frequently this makes its way onto physics exams and whatnot. Some students have a hard time, though, really convincing themselves that this is the case. So, how do we convince the skeptics? Well, in terms of instantaneous velocity, if you were to whirl something around your head and then try and release it to hit somebody who's in front of you, let's say you might be spinning around some sort of Nerf ball or something like that, at what point do you actually release this object? In other words, do you release it when it's in front of your head, or do you release it when it's to the side? Well, most people intuitively know that if you release it in front of your head, it's going to hit a wall, whereas if you release it to the side of your head, it actually ends up going straight. In other words, the second you let go of the string that's holding the object in a circle, it goes straight. So if you do it at the wrong time, well, sadly, if you're trying to nail a brother or sister, you're going to miss. So the conclusion, the velocity at any instant is tangent to the circle the object is forced to be in. Remove the force, that center-seeking force, and the object travels straight. Alright, acceleration centripetal. How do we do that? Well, we're going to try and demonstrate how acceleration centripetal acts towards the center using a pop from McDonald's and a Batmobile. I know. It's a cruddy drawing of a Batmobile, but it's best I could do. Alright, so in our first situation, you've pulled up to the drive-thru, you've ordered your pop, you have it sitting between your legs, and you look down at it. What does it look like? Well, with the Batmobile parked, the pop has a flat surface. In other words, the top of it is totally horizontal. Fair enough. Okay, here we go. So we then go and accelerate away from the drive-thru. So as you accelerate away in your Batmobile, what happens to the pop? Well, it sloshes backwards. Now you know that you're accelerating forwards and the pop's slashing backwards. So backward sloshing pop means a forward acceleration. Alright, now that you've accelerated away, you're traveling at a constant speed. Let's say on the highway, you're doing 27.3 meters per second. You look down at the pop, and what does it look like? Well, it's back to a flat top again. In other words, it hasn't sloshed anywhere. So constant velocity of 27.3, and you have a flat top again. The Joker steps out in front, puts some sort of bomb, big hole, whatever. You have to slam on the brakes. You slam it on the brakes. What happens? Well, the pop sloshes forward. Okay, forward sloshing pop. What does that mean? Well, it means that we have an acceleration that is actually backwards or in the opposite direction. Well, that's negative acceleration. It's kind of a tricky concept on its own. The easiest way I know how to deal with negative accelerations is actually if you plot a velocity time graph and just look at the negative slopes. What you notice is that there are two locations for negative slope. There's the top part, which means you're slowing down but you're still moving forward because you have a positive velocity, and there's the bottom part, which is a negative velocity, and you're actually speeding up. So in other words, you're speeding up backwards. So anyway, in this situation, we're in the top half. We're talking about a slowing down in the forward direction. I know that part's a little confusing. Anyway, back to our whole acceleration thing. So, pop sloshes forward because we're braking, and we're accelerating backwards. Okay, so now to summarize all this. If you have a constant velocity, you end up with a horizontal pop. In other words, it hasn't sloshed anywhere. If you have an acceleration, what we find is if the pop sloshes back, you're accelerating forward. If the pop sloshes forward, you're accelerating backwards. In other words, the moral of this story is that the acceleration is in the opposite direction that the pop sloshes. Okay, so now we're going to take our Batmobile and our pop into a traffic circle. So we go whipping around the traffic circle, let's say clockwise, and as you're in this traffic circle, you look down at your pop, and what you notice is that the pop has kind of shifted to the outside of the curve. In other words, it seems to be on the outside. Well, what does that mean to us? Well, what we came up with was if The pop sloshes one way, the acceleration's in the other. So in this situation, we have an acceleration that's actually pointing towards the center of the circle. Fair enough. It doesn't matter where you check this out in the circle, the pop always tends to be to the outside, which means the acceleration always is pointing towards the middle. Well, perfect. So intuitively, or the pop tells us that acceleration is always center seeking. Alright, there's another way you can do this. Kind of a quick and dirty way. It's using vector subtraction. Vector subtraction is kind of rare. We're used to vector addition, especially with vector arrows, the whole tip to tail thing. But anyway, here we go. So the acceleration formula is delta v over delta t. Delta tells us mathematically to go final velocity minus velocity initial over our change in time. Okay, well, what is VI and VF? Well, VI and VF are velocities at specific instances, some time length apart. So we can easily draw them on the circle with their tangent lines. They're the same length. We'll assume that they're going around this circle at the same speed. Now, the formula wants me to go velocity final minus velocity initial. I have my velocity final. That's not a problem. But I don't know how to subtract a velocity initial. I do, however, know how to add a negative velocity. Now, a negative velocity initial is the same length, just opposite direction. So now, how do we add vectors? Well, it's tip to tail. So we draw the first one, which is our velocity final. And then we draw tip to tail, the negative velocity initial. And then we draw a resultant, which goes from the very beginning to the very end. That would be the little blue line with the double arrowheads. And what you notice when you look at the resultant is that it's pointing towards the center. What is the resultant? It is the change of velocity. The change of velocity actually points towards the center. Now, this isn't 100% correct, but it's pretty close. Just quickly mention centrifugal force. It's not normally discussed, largely because centrifugal force is not a force acting on our object. It's our object acting on something else. Basically, if you were to go around a corner and you're on the inside of the corner and someone's on the outside of the corner, this is what's roughly going to happen. As you go around the corner, you are being held in that corner by the friction of the seat. If there's not enough friction, like someone arm rolled the seat, what typically happens is you want to actually go straight. Now, the guy on the outside of the corner, he's not just held by the seat, but by the car door. So he's going to do a circle no matter what. What that means ultimately is that your paths are going to cross. In other words, as you slide across the seat, because the car is turning underneath you, and then the guy on the outside stuck with the car, is that you're going to end up colliding and you're going to mash him into the outside of the door. Anyway, that's all I got. Centrifugal force, kind of an aside, but hopefully you kind of have a better understanding of how acceleration works. Thanks, bye.